Okay, recording. Hello, welcome to review session 2. Uh, Today's might be a bit shorter than last week's just because I feel like there isn't too much new content. I also covered a bit of it last week, but the things I'll go over today is I'll go over resistors in series and or just like components in series and parallel again. So stuff in series slash parallel. I'll go over source transforms. I'll go over voltage dividers, and I will touch on the delta to Y transform. Okay, so to start, I'll talk about components in series or parallel. So the most basic thing is, first off, I just want to touch on what series and parallel explicitly means, because it means one thing, each of them mean one specific thing, and just that. So things in series, things are in series when they are connected. If you think of like each component as having two sides, right? So this has two sides and this has two sides. Things are in series if one side of them is directly connected by a wire, and that's it. So, and there has to be just that wire, and that wire cannot split. So these two resistors would be in series. However, if I had a circuit that looked like this, now all of a sudden these two resistors are not in series because there is a branch. So that would not be in series. So to be in series, it has to just be a wire between the 2 points. Likewise, kind of extending that a bit, for things to be in parallel, you have to have both sides of each of them, each of your components, directly connected by a wire. So you have to be able to draw a path between both sides of the components without having to go through any other components. So, for example, something that would not be in parallel is if I had a circuit like this, right? And let's say I was told to simplify this. I've seen some students saying, oh, these two kind of look like they're in parallel, so I'm going to combine them over here. However, you cannot do that, right? So what's the thing for parallel? You have to have both sides connected by wire. For these two resistors here, this side is directly connected by a wire. However, on the other side, it is not, right? There's a thing here, so they are not in parallel. However, what you can do in this kind of scenario is you can see, okay, well, what did I say series is? Series is when you have one side directly connected by a wire with no intersections or anything. So here, these two are in series. So these two can combine into one resistor. So just kind of to show what that would look like, you could then turn that into a circuit that looks like this. And then it doesn't matter where you draw it, right? Because all that matters is the connections. So you could draw it like this, or you could draw it like this. As you can see, the connections are the same for both. Just to kind of make it a more meaningful example, I will leave it like this, even though that is usually not how I would draw it. However, now what would be the next step in simplifying this? You could say, okay, if I look at this, now these two sides are directly connected by a wire, and these two sides are directly connected by a wire. So these two are in parallel, and you can combine them with that formula. So for resistors, the like general formula is like R total equals 1 over R1 plus 1 over R2 plus dot dot dot, which then turns into like R total equals 1 over R1. And for the case where you have two resistances, and only for two, right? Because this is just how the math works out. You can do this a bit easier by it's like R1, R2 over R1 plus R2. So that's just a little convenient trick. And then for series, it's you just add them. That's how that works. Hopefully that's very review for all of you. And then the other thing I'll touch on is for current and voltage sources. Uh, Voltage sources will add in parallel or add in series. So like this, if this was 20 and this was like 4 and this was like 6, what we have here is, say, if you think about voltage sources as defining a difference in voltage from one side to the other, let's say we start at some arbitrary voltage here, I'll just call it 0, right? Here, we're going to 20 volts. Then here, we're going to 24 volts. And then here, if you notice, I drew this pointing the other way, so this would be subtracting. Now we'd be down to 18 volts. And what you can say is that, okay, instead of drawing out 3 voltage sources, this is exactly identical to just an 18 volt current, 18 volt voltage source. So voltage sources add in series. You cannot have voltage sources in parallel. It just doesn't really make sense. Like if I had, sorry, if I had a 2 volt source and like a 4 volt source, and I tried to connect them like that, this is just like not a thing you can do, because like if I say that this is 0 volts, then this one is defining that, okay, from here to here, I'm going up 4 volts, but this one's saying from here to here, I go up 2 volts. What's going to happen in practice is that like some crazy amount of current flows between them and they're going to get really hot and maybe bad things will happen. So don't do that. Current sources, on the other hand, are the opposite, where you can't put them in series. It doesn't really make sense to put them in series. You're not going to like the current can only be set once in the same way that the voltage can only be set once, you know? However, they add in parallel. So if I have like a bunch of current sources, right? Let's say this was 2 amps, this is 6 amps, and this is 3 amps. What we're going to have here is that this becomes one current source where it is 2 plus 6 minus 3, which is going to give us 5 amps. Because, you know, this one was pointing up, whereas these were pointing down. So this is kind of negative. Cool. Okay, I think that's all I'll talk about for series and parallel. The main thing that I want you guys to take away from this is series, they have to have no intersection. So if this is here, then it doesn't work. And for parallel, they have to be directly connected by a wire on both sides. If they're not directly connected by a wire, then they are not in parallel. Please don't get that wrong. Okay, what did I say I'll do next? Source transforms. Okay, source transforms are kind of straightforward. You'll do them in the lab, or you'll like learn about it in the lab a little bit. But the general idea is that if I have some circuit or some component of a circuit where I have a voltage source in series, remember what series means, meaning that it's just a wire between them and there's no intersection. So I have some voltage source and some resistance. And it has, we're gonna like say that it has 2 ends to this like section of circuit, right? We're saying that this is exactly equivalent to, mathematically, as a current source facing the same direction as that voltage source in parallel with a resistor. So you can see it's just changing what's inside that box, where it has the current and the resistance. The resistances are the same, and the voltage is related to the current by V equals IR. So this V, if you were going this way, it would be V equals IR, right? So you'd multiply these two. And then if we go the other way, it would be I equals V over R. So you'd divide this by this. And overall, what you get then is an easy way to convert between voltage and current sources. And you can kind of, depending on the problem, you can move that resistor from being in series to being in parallel, which hopefully should be pretty familiar with you guys by now, because you have to do that on your project. Okay. Yeah. So that's kind of all there is to it with these source transforms. You'll sometimes also see it drawn as like this. So hopefully you can see that this is the exact same circuit. It's just drawn in a different way, where again, all the connections are the same. It's just a different kind of orientation. So if you see it like this is the same thing. Oh, yeah, wait, no, that was right. Right. So yeah, the point is the thing that you have to make sure you're keeping track of is that the endpoints do not change. Everything inside the box changes. However, it should like rejoin back up before it goes to those terminals. So especially on like the first question of the project, don't mess up that. Because that one is drawn a bit differently and it can be a bit confusing as to where those connections might actually lie. Okay, next I'll do voltage dividers. So the idea with a voltage divider is that if you have some circuit or portion of a circuit that can be drawn kind of like this, where you have one voltage source and you have some resistors. You know from KVL, right, Kirchhoff's voltage law, that if let's just say for now this is 0 volts right here. If I have 0 volts here, then this is going to go up V volts here, and then it's going to have to go back down to 0 volts by the time we get here, right? Pardon my. What's the button? There we go. So the voltage has to go back down. And the way that works, right, is each of these resistors is going to have a voltage drop across it. And these voltage drops, so like the voltage will go down some amount here, and then down here, and then down here, and we'll be back at 0. And there's a very convenient formula we can use to find out what that would be. So let's just say VR1 in this case is going to be equal to, I'll call this like Vin just for making the math a bit more clear because I'm going to be writing V a lot. It's going to be equal to Vin times the proportion of R1 to the total resistance. Right? So this is saying the voltage across Vin, so the difference between the voltage at this point and this point is going to be this equation. The way you can think about that is like each resistor kind of gets voltage in proportion to its equal to its proportion of total resistance, kind of. The other way, where you are more likely to use this in a circuit where you have actually defined a ground, is let's say I wanted to find the voltage here, right? So what we can think about here is that, okay, this voltage here is equivalent to the voltage across these two resistors. And 0 volts is here. So we can represent this point, let's call this Vx, as Vin times the proportion of both of those resistors to the total resistance. Because you can think of these, if you mix them together into one resistor, it's the same kind of logic. And this is also something that you will probably be using on the quiz or on the project with the Wheatstone Bridge question. But yeah, this is just like a convenient shortcut that will make your lives easier a lot of the time. So practice it when you can. And yeah, and then what else? I said delta to Y transform. This is one of those things that they teach in the class and you use it once on a homework and then you never ever see it again. So I'm assuming it'll be like that again this semester, but I'll just really quick like write what it is. So if you have a situation where you have some kind of like T of resistors, in the same way that source transforms are like exactly identical mathematically, we can say that these two circuits are exactly identical mathematically, where we have give me a sec, it's going to take a minute to draw. So and again, the thing here is that the transform is only happening kind of inside of this box, and the points on the end will stay the same. So here, what was this labeled? I just literally looked this up on Google Images because I have used this so little that I do not remember the equations. However, you do have to use this on one of the questions on the project, so like have it up somewhere. But the equation is, if you're going in this direction, right, you have R1, no, wait, it's sorry, got RA equals R1, R2 plus R2, R3 plus R1, R3 over R1, and then RB equals, like, I'll just write them all out. It's going to take a second. But it's kind of just like you multiply all of them and then divide them by the corresponding resistor, like the opposite one. I also didn't write the R there. But you can see it's like kind of symmetrical. I do not have a proof for this off the top of my head, so you're kind of just going to have to trust me on this one. But it's something like that. And then going back the other way, it is RC over RA plus RB plus RC. And then it's symmetrical for all of them. I really don't want to write it out. If you're curious, look it up. Okay. And then one little shorthand I'll say, when you're doing this on the quiz or on the project, you are going that way, and all of the resistors are the same. So if R1 equals R2 equals R3, we can say that then RA equals RB equals RC, right? And that will end up equaling, let's just say this is R. Then just looking at the math, it'll end up being 3R, I believe. Because you'll have R squared plus R squared plus R squared over R. Yeah, it'll end up being that. Okay, and the last thing I said I'd go over is that. Okay, so those are the topics that I wanted to cover in terms of just making sure you guys have been told it. If you have any questions, speak up or say something in the chat. But then now I'll just do some practice problems for like 30 minutes. I might end a bit early today because I don't really have too many problems to go over. You haven't really learned too much new stuff. Next week, I'll be going over like mesh current and node voltage, which will take up a lot more time. But that stuff isn't really on this week's project, so I'm not going to go into that. But I'll go over some questions that might be somewhat relevant or good kind of practice problems for your projects. Okay. How should I go about explaining them? So there's a couple ways to do this. Let me actually write out what the question is. And I also will actually introduce another thing here because it's a shortcut for this kind of question, but it is not as straightforward as it may seem. So this question is saying find IX. So one thing I've been saying to people in office hours recently is that when you're in a circuit and it's telling you to find a specific value, in this case, it's the resistant or the current through this 12 ohm resistor, you cannot like do anything to this 12 ohm resistor. Because if you were to combine this with the 6 ohm resistor, then all of a sudden we have a new situation and this IX is no longer really valid. So we want to like leave this alone as much as possible. So I'll start by just going over what we can do without affecting that, right? And actually, yeah, there's two ways to do this. I'll go over the one that does not go over anything new first. So one other thing that I'm going to emphasize here is that when you have components in series, the like actual placement of them doesn't matter. So since this is in series with this, which is in series with this, like if you look at this as like one section, then you can like move the building blocks around as long as there's no like intersection, no node. But basically, I'll rearrange this a bit to a way that looks a bit nicer. Right? So then we'd have the 2, the 1, the 2, the 2, the 12, and the 6, and this is 40. And now we can combine this whole section together because that doesn't affect our current that we're looking for at all, right? So one quick trick is if you have two resistors in parallel that have the same value, the total resistance is just going to be half of that. You can see that from the formula where if we have 2 times 2 over 2 plus 2, right, this is going to be 1. Crazy. More generally, right, if you have r squared over 2r, that's what this is going to be, right? This is going to end up being r over 2. Cool. Algebra. So this is going to be have a resistance, total resistance of 1 ohm. And then we'll have these 3 in series. So it's going to be 1 plus 1 plus 2. Crazy. Then we will have 4 ohms. And we have our resistors. And we have 40 volts. And we had 12 and 6. And now we have to find that current. So the most kind of, let's see, what's the, yeah, so the way that you can do it, there's 2 ways you can do it. One way is find the voltage here. If we find the voltage here, then we can say, okay, if we like define this as 0 volts, we can find the voltage here, and then we can just do this voltage divided by 12, and we'll get the current. The other way is current division, which is like voltage division, it's just the logic is backwards. But either way, we do kind of have to like imagine or figure out what the equivalent resistance of that section is so that we can find kind of the total current through the rest of the circuit. So in that case, this is going to be 6 times 12 over 6 plus 12. I believe that'll get you 4. This trick here, this is like, it's not really a trick, but if you have like R and 2R, then you have R plus 2R. This is going to be 2R squared over 3R. That's a 4. 3R, which is going to be 2/3 R. So that's just another thing you can remember. If you're like, if you have like one resistor and then the other one is double that, then it'll end up being 2/3. Just a little shortcut you can remember. So you can say that this circuit is equal to having something like this, where you have 4 and 4, and this is 40. However, we can't really deal with the current going through the 12 ohm resistor anymore because we don't have that 12 ohm resistor anymore. But what we can do is find this voltage, and since things in parallel will have the same voltage, we know that this voltage and this voltage will be the same. So in that case, here we can do a voltage divider. So the voltage at this point, I'll call it Vx. Let's say this is 0 volts just so that our math is easy, right? We'll say Vx is equal to that 40 volts times 4 over 4 plus 4. It's just going to be 1/2 of that. So we have 20 volts. So now we can say this is 20 volts. And if this is 0 volts, then our I, our current that we're solving for, that Ix, is going to be equal to 20 over 12, right? Because we know the voltage here. We know the voltage here. This is 0. This is 20. It's just going to be that. And that's going to be a point. So this is a 10 over 6, which is 5/3, which is like, yeah, I don't know why I said 0 point. Not thinking. 1.67. Ha ha ha. Funny number. Okay. Yeah. That would be your thing there. So that's kind of how you can approach this, combining resistors, pretty chill, pretty cool. Next up, I'll do a question that's dealing with source transforms. There's some like pretty straightforward, simple questions here. This one's kind of a mix, actually. I'll do this one. So and this question is saying find the voltage on the 2 ohm resistor. So we're trying to find that. This is V2 ohm is what I'll call it. Using source transforms and combining resistors and such. So again, what I said in the last question holds, where we don't want to do anything to this resistor if possible, right? So while these two are in series, hopefully you can see that, if we were to combine them, then all of a sudden this 2 ohm resistor wouldn't exist anymore. So then we can't find the voltage across it because it's been combined with that resistor. So we just can't be doing that. So instead, we're going to have to start on the other side and do some simplifications there. Luckily, the question hinted using source transforms. If a question says to use a certain method, you do have to use that method to get full credit. So in this case, like even if you could think of something else to do, you got to use the source transform. So here, if I do a source transform on that section over here, we go back to where I defined source transforms for you, right? We have a voltage source in series with a resistor gets turned into a current source in parallel with that same resistor. So here, even though they're around a corner from each other, right, these two are in series, so we can do a source transform on that. So let's not modify any other part of the circuit, but then if we think of this and this as the endpoint, right, then we're going to end up with, instead of all this, we're going to now have this and this as the endpoint, right? But then we'll have a current source and a resistor. So it will look like, oh, and make sure when you're doing this that you don't accidentally flip the direction. So here, even though this current source is pointing down, that's the mode my brain was in, we see that it's plus on top. So the current source is going to point up here, which is important because that means that it's like negative kind of with respect to that other one. So in the current, right, I is going to be V over R, which is going to be 24 over 6, which is 4. So we have 4 amps here, and this is going to be 7 amps. And this hasn't changed. And now we can actually combine quite a lot, like right now. So I remember in the last question, I said things in series, you can kind of move them around. The same thing applies for components in parallel. So it doesn't matter like these two are connected here and they're like next to each other, so it's like pretty obvious that they're in parallel. But this resistor and this resistor are also in parallel. Remember, the condition for that is that the two sides of them can be connected by a wire, and in this case, they can be connected by just wires, because this is just wire this whole way, right? If there was, in this question, a resistor there, then all of a sudden, none of these would be in parallel, right? Like this and this would still be in parallel, but this current source and this current source would no longer be in parallel because there's a resistor here, and this would no longer be in parallel. However, since that resistor is not there in this question, we can combine these two resistors and we can combine these two current sources. So let's do just that. And I can't switch to black because I missed. There we go. So we now have 7 minus 4 is 3. Hopefully we all got that. And 6 and 12, I'll just write the math up here, but again, you can use that little trick I said on the last page. This is going to end up being, what, 72 over 18, not 20. I don't know what I'm thinking there. And that's going to be 4. So 4, 18, and 2. And now we're so close. We're almost there, right? If we now transform this back into a voltage source, then all of a sudden we'll have a voltage source. Like you can imagine if we were to transform this back, right? These are the endpoints. So then we'd have a voltage source and a resistor. And then this would be the circuit, right? And then this looks a whole lot like the example I gave for the voltage divider. And we can just do a voltage divider on the circuit to find the voltage across that 2 ohms. So now I'll do that. So here, going back in the other direction, remember V equals IR, you should know this one by now. V equals IR, so we're going to have 4 times 3, which is 12 volts. And the resistor stays the same. So we're going to have, let's say, that there, and then the direction stays the same, right? So since the current source is pointing down, now the voltage source is pointing down. This is going to be 12, 4, 18, and 2. And now last but not least, if we want to find the voltage here, well, one thing I will actually point out that is kind of not that important for this question, but it's good to pay attention to. In this question, right, this V2 ohms was defined kind of in the question as being positive on the top, negative on the bottom. However, if you look at this circuit we've actually ended up with, right, what we see is that the voltage source is pointing down, so the current will end up flowing this way, which means the voltage drop will in reality be in this direction. So what that means is even though we're going to do a voltage divider, the voltage is kind of, you're going to get a negative if you were looking at it in this direction. So you can still do the same math, however, you should just put a little negative on the end because the voltage that we are finding from the voltage divider will be assuming that the voltage drop is that direction. However, the question asked for a voltage referenced like this, right? So you have to put a negative on it. So anyway, we can represent that as negative V2 ohms is going to be 12 times the resistance we're looking at over the total resistance. I should rewrite this slightly so it's more clear that this is the 12 volts. And then we're going to get negative V2 ohms is equal to 12 times 2 over 24, which is 1/12, right? Yeah. So it's going to be 12 times 1/12, which is 1, is negative V2 ohms. So then V2 ohms is going to be 1 volt, and that would be your answer for this question. And by 1 volt, I mean negative. There you go. Cool. So that's kind of how you can use source transforms to simplify circuits. Sometimes you have to go back and forth. In fact, you have to do that like 4 times in one question on one of the questions on your project. Yeah. What else did I have prepared here? Honestly, not too much. This one looks kind of similar, but I'll do it. Okay. Source transforms, yeah. Oops. And like honestly, this is kind of that if you understand how to do this, that's kind of the whole project for this week. So you should be pretty set. This might be the last one I do, unless the few people that are actually in the Zoom call have any questions, but and this is saying find find this voltage V. And pardon my handwriting, that was supposed to be a big A. So this is saying find this voltage. So to do that, we basically just have to simplify the circuit a lot until we have something that we can work with. Generally, like a good bet is just simplify the circuit, especially if it says to use source transforms, like use source transforms. So here, again, we don't want to mess too much with this side. However, we actually can in this scenario because remember, things in parallel have the same voltage. So even if we were to source transform this, right, you can think of like this as the endpoint of the source transform. And since it's a wire, like this whole top, right, this whole section here is going to stay the same. So after the source transform, right, the voltage between these 2 points will be the same. It's just instead we'll now have something that looks like this between them, right? However, the voltage will still be that voltage V that we want to deal with. So we can do that. And we can also source transform this. And then that will actually end up getting us to a pretty good place. So let's show why that is a good thing. And then hopefully you're all familiar with like SI or like SI prefixes. Kilo is 1000, milli is 1000th, or like 0.001. And conveniently, when you multiply kilo and milli, you just get like normal numbers. So anyway, if we source transform this left one, you're going to have 6 milli times 1.4 kilo, which is going to be 6 times 1.4, which gets you just normal 8.4, because V equals IR, right? And that's going to be in series with that 1.4 kilo ohm, and this is 8.4 volts. And then we have that 600 ohm thing here. And then here we have our voltage source pointed down and our resistor. And the resistor is 3 kilo ohms. And here we have 3K times 1 M or 1 milli, and that's going to just be 3. Crazy. And we're still trying to find this voltage. But now we're almost, it's like pretty chill now, right? Because this is just one loop. And with one loop, you can do things pretty easily. Sorry. There's like a couple ways you could go about this. I think the most straightforward way with it, you don't have to do any more source transforms if you do it this way, right? You could find the current through this loop, and then with that current, you can get the voltage here, and then you just add that to the voltage here. You could also do it with another source transform. If you hadn't transformed this one to begin with, right? You could combine these and then source transform it back into a current source and then like add it to this current source. But I like the way I'm doing, so I'm going to do it that way. So here, if we want to find the current throughout the loop, the current is going to be the total voltage over the total resistance for a loop, because you can imagine you could combine all of these things in series. And in that case here, it's going to be 3 plus 8.4 over 600 plus 1.4K plus 3K, which is going to be like 11.4 over 5,000, 5K, which is not a nice number, but I'll put it in my calculator and see what I get. Over 5, it's 2.28 milliamps, right? So now if we're only, now that we found that, right, we know there's 2.28 milliamps here flowing through here that will create a voltage across that resistor. So let's say V3K equals 2.28 milli times 3K. So if I do that, yeah, that's going to be 6.84 volts. And now how does that relate to our voltage that we were trying to find originally? Well, let's look. So it was defined in that direction, right? With the plus on top and the minus on bottom. Here, we just found that this is 6.84 volts here. However, this voltage source here is defined in the other direction. So if we want to find the total voltage from this point to this point, it's actually going down 3.8, or it's actually, sorry, it's going up 3.8 volts. I can't speak. It's going up 3 volts and then down 6.84 volts. So you would actually need to subtract these. So then our V is going to be our 6.84 minus 3, and that would get us 3.84 volts. And that would be your answer. Cool. Yeah. And then I'll just do like, since I have time and I feel like I should fill it, I'll do one more like pretty easy source transform question. Shouldn't take too long. Yeah. So this is saying find the power of the 10-volt source. So before we get started, what does that mean we have to actually find? It means we have to find, remember, power is current times voltage. We already know the power, or we already know the voltage of the 10-volt source, right? It's just 10. And then that just means we have to find the current of the 10-volt source. So what current, we don't actually know what direction, but we have to find that current and then just multiply it by 10. So to start, probably be best to do some kind of source transform because that looks like the easiest way to go about this. So I'm just going to kind of go fast through this one. So if I source transform here, right, we're going to have 20 over 10, which is going to get us 2 amps in parallel with that 10 ohm resistor, in parallel with that 5 ohm resistor. And then that is with the rest of the circuit still there. If we then combine these two resistors, right, we're going to end up with 10, it's going to be, 10 times 5 over 10 plus 5. It's 50 over 15, which gets you like 10 thirds or 3.33. Yep, 3.33. And then we have 15 here and then 10. And remember, we're trying to find this current. That's our goal. So if we make this one loop, then that's pretty easy. So we're going to source transform it back again. So we end up with, remember, V equals IR. So V is going to be 2 times 3.33, which is going to get us 6.67 and that 3.33. And then 15, and then 10. And now, successfully, without having to change any of the circuit, we have found that we've gotten in one loop, and now we can find the current. And the current here, that's part of the circuit, has never changed. So that initial current we were trying to find is still the current that we will actually get here. So what is going to be that total current? So let's define the current as flowing, I don't know, that way or something. So the way that you should look at this actually is you see that 10 volts is bigger than 6.67 volts. So it's going to flow from like in this direction because this voltage source is like more powerful and it'll overwhelm the other one, I suppose. So we're going to say the current's flowing that way. And what will that current be? In the same way it was in the last question, it's the total voltage over the total resistance. Here, the voltage sources are against each other, right? You can see that because it's going up in this direction and then down in this direction. So like here it's minus to plus, but then here it's plus to minus. So it's, this one it's going to go up and then this one's going to go down. So we can think of this one as negative is the conclusion there. So it's going to be 10 minus 6.67 over 15 plus 3.33. That's going to be equal to a current of like 0.1. My stream failed. Give me a sec. Let me reshare my screen. I don't know why that happened, but it's fine. Okay. So this is 0.1818 ... amps. And now that we have that, it's flowing in this direction, right? So is that power going to be positive or negative? Well, it looks like this is going to be supplying power. The other way to look at it is, remember your like passive sign convention. We have a voltage rise in the direction of the current, which means that this is a negative power. So our power at the end of the day is going to be 0.182 times 10, and it's actually going to be like negative. So then we get that our power is going to be negative 1.82 watts. Wow, so cool. And again, this question, you just use your source transforms to simplify the circuit until you have something that's easy to work with, easy to find the current. And yeah, I think I will end it here. Don't really think there's much point in me doing more practice problems. Like, you just got to know. I think the main takeaways from this are make sure you understand when things are in series and when they are in parallel. With the parallel, you want to make sure that both sides are directly connected by wire and there's nothing between them. And with series, if there's a junction, they are not in series. They have to have just one path between them. And remember your source transforms, they're pretty useful. And voltage divider is useful. So yeah, if you haven't finished your project yet, good luck on that. Otherwise, I don't know. Have a nice rest of your week.